Okay, so this is our molecule building lab. So first thing we need to do is check all of our materials. It says 3 4-holed black spheres. So here they are. Notice that they have 1, 2, 3, 4 holes. Okay, so that means it can make 4 bonds. We've got 3 of those. 4 1-holed black spheres. So there's 1 hole here for 1 bond. 4 of those. 4 rigid bonds. Rigid because you can't move them. And then 4 of the flexible bonds. So when we build something with a multiple bond, like a double or triple bond, we're going to need to use these. So double bond, we'd use 2 of these. Triple bond, we use 3 of these. Okay? And then the last ones are these paddles. Some people in the room have, they look like wasp nests. So these are what we're going to put in when we don't have a bond. Instead, we have a lone pair of valence electrons. Okay? So the first thing we have to do is CH4. CH4, so obviously this will have to be carbon because carbon forms 4 bonds. And these are going to be the hydrogens. Hydrogen can only form single bonds, so we have to use the rigid bond. And so we don't have to worry about, well, where do I put it? Where do I put this? Well, because it tells you. There are only certain places you can put that bond because there are only certain holes. So here we have this coming out. Okay. And here. So here is our CH4 methane. Okay, so I'll help draw it. It's kind of weird. I'll put my C in the center, and then 1, 2, 3, 4 bonds, right? Now, I'll admit this doesn't look exactly like my drawing. It looks like I stepped on it, squashed. H, 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 H. That's okay. All right, so here we have that. Okay, now you are going to have to decide what the molecule shape is, what the molecule polarity is, and what the bond polarity is. So let's try to zoom in a little bit. Molecule shape, you have to look at your notes, but you're looking for things like linear, could be an option. Tetrahedral could be an option. Bent could be an option. And pyramidal can be an option. Now remember, there are other molecule shapes out there in the world, but we're just not getting to them. Okay? So then you're going to decide which of these shapes this is. Molecule polarity. Molecule polarity has to do with symmetry. Symmetry. So if you are symmetrical, that means your molecule is nonpolar. If you are asymmetrical, your molecule is polar. So you would look at your molecule, and I will make sure I rotate it around. So look, look, look. Does it look the same no matter how I turn it around? Or does it look different? If it looks the same, you call it nonpolar. If you think there's a difference, you call it polar. Okay? The last one is bond polarity. This has to do with electronegativity differences. So where do we find electronegativities? Electronegativities are found on reference table S. So in the case of this, I have a bond between carbon and hydrogen. Yeah, I've got 4 of them, but they're all the same. So then I would look up the difference of electronegativity between carbon, hydrogen, and I would subtract them, obviously. That's what difference means. It means subtraction. Remember, 0, a difference of 0 will be nonpolar. Between 0 and 0.5, we call that slightly polar. 0.5 to 2 is polar, and anything higher than 2 we call extremely polar. So SP would be slightly polar, polar, extremely. I know there's some overlap with 0.5, so let's just call this 0.4, and 0.5 would definitely mean the polar range. So you have to look them up on table S. Okay? So I'm not going to do those for you. You're going to think about those yourself. All right, so now, here's my last for the CH4. NH3. So NH3 is almost the same. So now we're going to pretend that this is nitrogen, not carbon, and we have our 3 hydrogens, and everything's great, except, can you see it? There's a hole here. We're not going to put a bond there. Instead, we're going to put our lone pair, because that's what it is. So I'm going to put my lone pair in here. And maybe you remember what the lone pair does. It repulses everything back, so you squeeze them a little bit together. You squeeze them. Okay? So now let's draw it, and then I'll rotate it around a little bit for you. So N is here. You've got your boop boop lone pair, which repulses the other bonds downward. Okay? Okay, so, and remember, it's not nice and even. We gotta squeeze these a little bit. Let's talk about the shape of this. The lone pair at the 12 o'clock spot provides it its shape. Check your notes. Okay, molecule polarity. Is it symmetrical or not? Take a look. Does it look different when I rotate it around? If it looks the same, you call it nonpolar. If it looks different, you call it polar molecule. Then with bond polarity, you would have to figure out the difference in electronegativity between the nitrogen and the hydrogen. And you look that up on table S and use the chart. So you subtract those values and then you see which one it is, okay? Oxygen molecule. Oxygen molecule, double bond. Okay, that's in our notes. So we have to use these, and we have to use the bending bonds. So double bond, okay? It forces us to bond in a certain way, okay? Now what? Are we done? No. No, we're not done. So we need to add in our lone pairs wherever there's an empty spot. Doop. 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 Okay, weird. All right, let's draw that. Double bond, but we're not done. You have to indicate the presence of the bond, or the lone pairs. So 11 o'clock, 7 o'clock, 1 and 5, I'd say. Okay? Molecule shape. Linear, tetrahedral, bent, pyramidal. Check your notes. Use your resources. Molecule polarity. Does it look symmetrical or does it look asymmetrical? If you chop it down one axis, does it look the same? If you chop it down another axis, does it look the same? Okay? Finally, the bond polarity. The electronegativity difference between these two atoms. This is an oxygen and this is an oxygen. Find those electronegativity values on table S, subtract them, use this chart. The next one is a nitrogen molecule. That's a triple bond. Triple bond. So guess what? I can use this, and then I just need to make a triple bond. So if I take two of these lone pairs out, it forces me, it's challenging. Oh, triple bond. Okay. Triple bond. How do I know nitrogen's a triple bond? We've talked about it. Okay. But remember, that's not all. Remember, you can't have those empty holes. We have to put in our lone pairs. Because of the rigid structure of the triple bond, the lone pairs are going to be as far away as possible. So 9 o'clock, 3 o'clock. Okay? Let's talk about molecule shape. Linear, tetrahedral, bent, or pyramidal. Let's talk molecule polarity. Does it look symmetrical? If it does, you say nonpolar. If it's asymmetrical, you say polar. And finally, bond polarity. You find the electronegativity differences between a nitrogen and a nitrogen, wink, wink. Subtract those values and then figure out what kind of a bond this is. H2O is water. This looks like water, except holes. Can't just leave them gaping holes. Got to put in your, there we have our lone pairs. Now I will admit, you've probably seen water illustrated like this. Something like that, like a Mickey Mouse, where these are the H's. Wow, the Sharpie's dying. And then this is the O. But that's not the full story, because look, why did you have that strange shape? Because of the two lone pairs. Okay? That's what chemists know that the normal person does not. So how are we going to draw this? Oxygen, a bond to hydrogen, a bond to hydrogen. Why is it bonded like that? Because of the lone pair. We can call it at 5 and 7. You could also have drawn, this is how I did it. You could also have drawn water like this, where you have the two H's below. You could also draw it like this, to the right. It doesn't matter, because again, molecules rotate in space. But just don't forget, the two lone pairs. Molecule shape. Does it look linear? Does it look pyramidal? Does it look bent? Does it look tetrahedral? Check your notes, check your resources. Molecule polarity. Does it look symmetrical? Chop it one way, maybe it looks symmetrical. Chop it another way, does it still look symmetrical? Look at me rotating it around. Does it look the same or not, depending on how you lay it down? Finally, bond polarity. You're going to check out what is the difference between a hydrogen and an oxygen. Okay? Last one is carbon dioxide. So oxygen would love to form a double bond if it can, and guess what? It can with carbon. So I'm going to have to use all three of my black spheres. And so here I have, this used to be nitrogen, but now I'm going to make it, my carbon dioxide, and I apologize that all of these are the same color. So let's just pretend that this is our carbon because it's in the center, two oxygens out here. Carbon forms 4 bonds. Oxygen likes to form double bonds, but we've still got some holes left over. What goes there? The lone pair. Okay. Wow, check it out. All right, that's something to behold. So we have a carbon in the center, which has our 4 electrons, but instead of going, around, we're going to have 2 on this side, 2 on that side to form the bond with oxygen. But don't leave it like that, because remember, we've got the lone pairs. 11 and 7, 1 and 5. This is 2 dots. That doesn't look like 2 dots. I'm going to make it with 2 dots. There we go. Okay? Look at the shape. Linear straight across, tetrahedral where you've got a central atom and 4 bonds, bent, or pyramidal with the lone pair repulsing downward. Symmetry. Can you chop it down the middle and it looks the same? Can you chop it down another axis and it looks the same? Or does it look different? Yes, I know this goes up and this goes down and these go side to side, but You have to remember that molecules are moving around in space. Is the shape the same? Finally, the bond polarity would be between a C and an O. So go ahead and check out those electronegativity values and do your subtraction. Then determine what kind of bond polarity it is depending on the value you get. Okay, if you have questions, please reach out. Good luck!